So if I'm going to cool something, so let's say I have something at 100 degrees Celsius. So temperature. Oh, okay. Put it there, in Celsius. And time, in seconds. If I put something that's 100 degrees Celsius in the middle of this room, how cold can it get? What's the coolest it's going to get?
Room temperature.
Yeah. So whatever it's going to cool to, whatever we do here, it's got a limit. So room temperature, roughly 20 degrees Celsius. It won't drop below that, statistically speaking. I've not subjected you to this, but I will now. With thermodynamics, typically it's understood that after every sentence you say, statistically speaking, is assumed. Because all thermodynamics predicts is what's going to happen on average. It doesn't predict small little fluctuations. So it is possible in the middle of summer here for all the water to freeze. Odds are way against it. So statistically speaking, it's not going to do that. But there is a non-zero probability that it could happen. All right, so if it cools, the temperature is going to drop off, and it'll get closer and closer, and eventually it gets so close to the room temperature that you can't tell the difference. This curve right here. Well, we're not going to go through the math of it. It involves natural logs or the natural exponent, which some of you have seen, some of you have not. What it turns out is that the change in temperature over the actual change in temperature over the change in temperature that's possible is a constant. Within the same time unit. All right, what do I mean by that? Take my aluminum block starts, or I have an object that's at 100 degrees Celsius, room temperature, so this is T initial, room temperature, we'll keep it 20 degrees Celsius. So it could lose 80 degrees, that's how much temperature I have to give up. After 1 hour, the temperature is now, we'll just say 80 degrees Celsius. So after 1 hour, that's the temperature. The question is, after 2 hours, what is the temperature? Now, it's not going to lose, it lost 20 degrees here, it's not going to lose 20 degrees in the next bit. All right, so the amount that it actually did lose was 20 degrees. The amount that it could have lost is 80 degrees. So in 1 hour, we set up this ratio of the amount it did lose over the amount that it could have lost. Do the fancy math, and you get 0.25. What Newton's law of cooling states is that's going to stay constant. So now it's 80 degrees Celsius. And we have to figure out how much it's going to lose. Well, I know it's going to lose some temperature. The amount that it possibly could lose, well, I got 60 degrees Celsius, it could still lose. And that's going to be equal to the same fraction, 0.25. So the math problem is x over 60 is equal to 0.25. That's the math problem, or over 1 if you like.
15.
So x is 15 degrees Celsius. And so after 2 hours, and so it loses 20 there, minus 20 degrees Celsius, and there it's going to lose 15 degrees Celsius. So it's now 65 degrees Celsius. After 3 hours, so 3 hours. Well, it's now at 65. What's the most it could possibly lose? Again, we're assuming that the room temperature doesn't change.
45.
Yeah. So the amount that it actually will lose in the 3rd hour, out of the possible 45 it could lose, it's going to be equal to 0.25. So when we change the temperature is 1.25.
Yep.
So I would now be at, doing the fancy math again, sorry,
53.75.
75 degrees Celsius. What the heck, let's do one more. And then we'll see if we get that curve I was sort of thinking we'd get. After 4 hours, well, again, how much could I possibly lose?
31.75.
Yep.
33.75.
So I'm here, that's the most I'm gonna lose, or that's the far lowest I can get. So 33.75, still equal to that same fraction we started with.
8.4375.
8.4375,
75.
so that's the amount I'm gonna lose. So that minus 8.4375, which is 39 point something. What is it? 53.75 minus 8.73, so 8.4375.
45.3125.
Oh, okay. 45 point what?
3125.
Let's see what that plot looks like. Let's see, the color that will show up, I think will. So I've got the temperature right here. Got the time right there. I'll make that 1, 2, 3, 4. That's only as far as I went. Let's try that out. So 1, 2, 3, 4. So this is time in hours. This will be temperature in degrees Celsius. 7, 8, 9, 10. So put that in 100, 10, 20, 30. All right, so I know I start out at 100 degrees Celsius. At 1 hour, I'm at 80. At 2 hours, I'm at 65. At 3 hours, I'm at 53.75. At 4 hours, I'm at 45 point something, so somewhere around there. So hopefully you can see that there's this trend here that's starting to sort of curve downwards. You don't, eventually it's going to get closer and closer to 20. So as each hour passes, less heat is lost. All right, questions to hear? now, I'm gonna grab calculators, I'm gonna put a problem on the board, and you're going to solve it and dazzle me. So let me grab the calculators. All right, so we're gonna start out with our favorite aluminum block. Let's see if that was 160, all right. So 60 degrees Celsius is the initial temperature. Room temperature, the room is 20 degrees Celsius, because I have no imagination there. After 5 minutes, it is 50 degrees Celsius. After another 5 minutes, so total of 10 minutes, after another 5 minutes, what is the temperature? And if you need a calculator,
Don't forget on the wizard test, don't forget units. That wise, yeah.
Yeah.
that's how much it lost. There's two parts. One is figuring out what is the change temperature, but the actual question is, what is the temperature? So it's okay to subtract it. I've seen a number of people make the same mistake. When you're setting up the fraction, figure out what that constant is. It's the actual change in temperature over the, I guess, maximum change in temperature. So the actual change in temperature, I went from 60 to 50. The actual change is 10. Technically negative 10. And the best you could lose is 40. So that's the fraction you're dealing with. A number of people had 0.2 over, or 20 over 50.
Because in the first problem, that's what you did. And that-
Yeah, I chose bad numbers there. No, that 20 degrees right there
It wasn't for the room temperature?
is because it went from 100 to 80.
Okay, that's where you get confused. 'Cause
Yeah.
that's when you get-
And there I was accusing you of picking bad numbers, and, yeah, sorry about that. And the, man, this is pretty much just the type of thing that he did. And the 80 here comes from the fact that that difference is 20, or sorry, that difference is 80, not that. That,
Look at you.
all right, that again. All right, let's take a look at this one. I'll give you another one with hopefully fewer issues. The answer is 42.5 degrees Celsius. So the fraction is 0.25, and so now on here, I could lose 30 degrees Celsius. I actually lose, well, that's what I'm trying to figure out. It's equal to 0.25. And so X is, it's mathematically negative 30, so negative 7.5. Was not too worried about the plus and minus because it's cooling off, so you should know it's losing that amount. So we end up with 50 minus 7.5, which is 42.5. All right, different numbers with a different fraction. It'll be epic. No, I'm not doing that one. So my initial temperature of this object is 70 degrees Celsius. The room temperature is, so keep the same numbers here, 10 degrees Celsius. After 3 hours, the temperature of the object is 50 degrees Celsius. Is it really what I want? Yeah. So 3 hours later, or after 6 hours, what is the temperature? Yes, question?
Yeah, when you say object, that's, or when you say initial temperature, that's the initial temperature of the object.
Yes.
Okay.
Yeah. In this whole scenario with the neutral level cooling, we have to assume that the environment stays constant. All right. Time to dazzle me again.
round off the fraction to just 0.3.
Yeah, no point three, I did three.
Okay.
So.
Yeah. That's the most it could lose.